On August 22nd, wind gusts in Riga exceeded 108 kilometers per hour. Trees came down onto power lines, transportation was disrupted, and flights were delayed or rerouted. More than 250,000 customers lost electricity in Latvia, more than 200,000 in Lithuania, and over 100,000 in northeastern Poland. 2 people were killed, one in Latvia when part of a building collapsed in Jelgava, and another in Lithuania after a tree fell. At some weather stations, roughly half of a typical month's rainfall fell in a single day. For the region, this was not simply a wet day. It was a powerful cyclone whose effects were felt across several countries. And the contrast is striking. While the Baltic region and parts of northeastern Europe had often been on the cooler side of Europe's temperature pattern in July, the western part of the continent had been living through a very different summer. Repeated heat waves, moisture deficits, wildfires, and exceptionally warm coastal waters. Europe was experiencing several weather regimes at the same time. By late August, attention had suddenly shifted toward a powerful cyclone over the Baltic region. How can one continent move between such dramatically different weather conditions in such a short period of time? That is not a rhetorical question, and it does not require a sensational answer. It is a question about how the atmosphere above Europe actually works, and why the boundaries between completely different weather regimes can sometimes move so quickly that the change feels almost instantaneous. To understand it, we have to look beyond what is happening at ground level, where we feel the wind and rain. We also have to look several kilometers above us, where vast currents of air move across the planet, invisible from the ground, but crucial to almost everything happening below. Start with August 22nd and 23rd. A low-pressure system developed over the North Atlantic and moved east toward northern Europe. By the time it reached the Baltic Sea, the system had deepened. In meteorological terms, that means pressure near its center had fallen, increasing the pressure gradient between the center of the low and the surrounding atmosphere. That gradient matters because wind is driven by differences in pressure. The stronger the pressure change across a given distance, the stronger the resulting flow can become. In the northern hemisphere, the rotation of Earth bends that moving air, producing the counterclockwise circulation associated with a low-pressure system. In Riga, gusts exceeded 108 kilometers per hour. At several stations, rainfall totals approached half of what would normally fall during an entire month. Across Latvia, Lithuania, and northeastern Poland, falling trees and branches damaged power lines over a wide area. Roads and railways were obstructed. Riga Airport warned travelers about possible disruption. Heavy rain persisted in Estonia, even after the strongest winds had moved through neighboring countries. Authorities urged people to stay indoors where possible and to avoid fallen trees and damaged electrical infrastructure. Even after the strongest gusts weakened, the danger did not disappear immediately. In one sense, this was another extratropical cyclone, one of many systems that cross the North Atlantic and Europe every year. But its impacts were severe enough to make it worth asking a larger question. Why can late summer in Europe produce such sharp contrasts between heat, drought, intense rainfall, and damaging wind? To answer that, we need to step back from a single storm and look at the wider summer of 2026. The June to July period in Western Europe was the warmest in the ERA5 record beginning in 1979. The regional average reached 21.62 degrees Celsius, 2.79 degrees above the 1991-2020 average. That does not mean every part of Europe was unusually hot at the same time. It means that Western Europe, taken as a region, experienced an exceptionally warm background over those 2 months. France also faced widespread drought concerns. Prolonged heat and dry soils increased wildfire risk in several areas. By mid-August, even a fire in a nature reserve in eastern Belgium attracted attention, precisely because the region is better known for a relatively wet climate than for major summer fire risk. The comparison with earlier hot summers is useful, but it also needs care. Europe has experienced severe heat before. The summer of 2022, for example, brought repeated heat waves, widespread fires, and a large burden of heat-related mortality. What makes 2026 notable is not that heat suddenly appeared in Europe for the first time. It is that the temperature background in parts of the continent continued to reach the upper end of the modern observational record. The lack of moisture was visible not only in soils. Water levels fell in lakes and rivers in parts of the continent. In Hungary, one of the country's largest lakes dropped to exceptionally low levels by early August, exposing areas of shoreline that would normally have been underwater. But at exactly the same time, other parts of Europe were receiving abundant rainfall. That distinction is essential. Europe is not one weather zone. A heat wave in France does not mean Finland is experiencing the same conditions. Drought in one region can coexist with flooding in another. The atmosphere does not impose a single weather state on an entire continent. And there is another part of the story. While the land was warming, the seas surrounding Europe were also unusually warm. Parts of the western Mediterranean, including waters near the Gulf of Lion and around the Ligurian and Tyrrhenian seas, experienced exceptionally large sea surface temperature anomalies during the summer. For seawater, which changes temperature much more slowly than the air above it, persistent anomalies of several degrees are significant. During the first half of 2026, the average surface temperature of the Mediterranean remained among the highest observed in the modern record. By July, large areas of European waters were experiencing marine heat wave conditions. At individual locations, open water temperatures reached values that would normally be associated with much warmer climates. The precise numbers varied from one basin and one day to another, but the broader signal was clear. Large areas of water surrounding Europe were holding an unusual amount of heat. A marine heat wave is a sustained period during which ocean temperatures remain unusually high for a particular location and time of year. During the summer of 2026, these conditions appeared across several European marine regions, including the western Mediterranean, the Bay of Biscay, and Atlantic waters near Europe. Why does that matter for weather? Not because warm water automatically creates storms. It does not. But the ocean helps establish the temperature and moisture environment through which weather systems travel. To understand the connection, it helps to return to the cyclone itself. An extratropical cyclone is, in simplified terms, a vast atmospheric system that develops where air masses with different temperatures meet. Along the boundary between relatively warm, moist air and colder, denser air, fronts form. Warm air can be forced upward over colder air. As that air rises, it cools. Water vapor condenses into cloud droplets, clouds deepen, and precipitation develops. A mature cyclone is therefore not simply a spinning patch of bad weather. It is a three-dimensional system that transports heat, moisture, and momentum over enormous distances. As a cyclone develops, its cold front often moves faster than its warm front. Eventually, the cold front can catch up, lifting the warm air away from the surface. Meteorologists call this process occlusion. Around this stage, a cyclone may be close to its mature phase, with strong winds and widespread precipitation concentrated around different parts of the circulation. That helps explain why the impacts of a storm can be intense but relatively short-lived. A particular location may experience the strongest winds for only a few hours, even though the full cloud system extends across hundreds or thousands of kilometers. Now we can return to the role of temperature and moisture. Warmer air can contain more water vapor than colder air. This is basic atmospheric physics. A warmer sea surface can also support greater evaporation when the surrounding atmospheric conditions allow it. That adds moisture to the lower atmosphere. If moist air is then lifted along a front, inside a developing cyclone, or through another mechanism, the water vapor can condense and produce heavy precipitation. This is one reason a warmer atmosphere can increase the potential for intense rainfall. But potential is not the same thing as outcome. Actual rainfall depends on the structure of the storm, how quickly it moves, how efficiently moisture is transported into it, the vertical motion inside the system, and where its frontal rain bands develop. That is why rainfall inside a cyclone is rarely distributed evenly. One location can receive an extraordinary amount of rain, while another, only a relatively short distance away, receives much less. Moisture is often concentrated into corridors and bands. Where those moisture streams intersect strong upward motion, rainfall can become particularly intense. This helps explain why some stations in Latvia received around half of a normal month's precipitation in one day, while nearby areas experienced less extreme totals. The pattern is not a uniform blanket. It is closer to an irregular moving structure, with narrow zones of much stronger precipitation embedded inside a larger storm. And this is where an important distinction has to be made. Warm water does not create an extratropical cyclone by itself. It can provide additional moisture and alter exchanges of heat between the ocean and atmosphere. But the development of these cyclones is driven primarily by atmospheric dynamics, especially horizontal temperature contrasts and processes higher in the troposphere. The sea is part of the environment in which the storm develops. It is not a simple on-off switch. For the same reason, we cannot say that the Baltic storm of August 22nd and 23rd was directly caused by climate change. Making that claim about one specific event requires an attribution study designed to compare the likelihood or intensity of the event in today's climate with a hypothetical climate without the same human influence. At the time of this documentary, no dedicated attribution study for this specific Baltic storm had been published. That does not mean climate change is irrelevant. It means the question has to be framed correctly. We have strong physical and observational evidence that a warmer atmosphere can hold more moisture, and that warming is changing the background conditions in which weather events occur. There is also evidence linking human-caused warming to the increasing likelihood and intensity of many marine heat waves. But those broader conclusions are not identical to saying that one particular cyclone was caused by climate change. Those are two different scientific statements. Keeping them separate is not unnecessary caution. It is how we distinguish what the evidence already supports from what still requires event-specific analysis. The marine heat wave itself also matters for reasons that have nothing to do with storms. Persistently high water temperatures can reorganize marine ecosystems. Species that tolerate warmer conditions may gain an advantage or expand into new areas. Other organisms, particularly those fixed to the seabed or unable to move quickly into cooler water, can experience severe thermal stress. Changes in jellyfish abundance, impacts on seagrasses and algae, and stress on marine invertebrates can all become part of the ecological response. So, unusually warm European seas are not merely colored areas on a temperature map. They represent a real change in the physical environment experienced by marine life. But temperature at the surface, on land or at sea, is still only part of the weather story. To understand why the atmospheric pattern can change so quickly, we have to go higher. Roughly 9 to 12 kilometers above the surface, near the upper part of the troposphere, fast currents of air circle the planet. One of the most important for European weather is the polar jet stream. The jet stream is a relatively narrow corridor of strong winds moving generally from west to east through the middle latitudes. You cannot stand outside and see it, yet its position can strongly influence which regions receive Atlantic storms, which remain under high pressure, and where colder or warmer air masses are able to move. The jet stream exists in large part because of temperature contrasts between lower and higher latitudes. But it is rarely a perfectly straight river of air. It bends north and south in enormous waves. Meteorologists call these planetary scale features Rossby waves. Where the upper-level flow arches northward, a ridge may form. Where it dips southward, a trough develops. Those features are closely connected to the pressure patterns and storm tracks below. Usually, the waves progress and change. Weather systems move. A period of sunshine gives way to cloud. A low-pressure system passes, and another pattern replaces it. But sometimes, the large-scale flow becomes much more persistent. A ridge can remain in roughly the same region for an extended period. Surface high pressure can become difficult to dislodge. Atlantic weather systems may be forced to travel around the blocked region rather than directly through it. This is what meteorologists mean by atmospheric blocking. During hot episodes in Western Europe in the summer of 2026, blocking high-pressure patterns were an important part of the atmospheric setup. Under persistent high pressure, sinking air suppresses cloud formation. Strong summer sunshine heats the surface. Soils dry. Once the ground loses moisture, less incoming solar energy is used for evaporation, and a greater fraction can go into heating the surface and the air above it. That can reinforce heat locally. At the same time, Atlantic fronts that might normally bring rain can be diverted northward or around the block. The result is a striking continental contrast. One region can sit beneath clear skies and persistent heat, while another, only hundreds or a few thousand kilometers away, experiences repeated rain and wind. This is why statements such as "Europe was hot" or "Europe was wet" are often too simple. Europe can be both at once. The important question is where the boundaries between those regimes are located, and whether they are moving. No blocking pattern lasts forever. Eventually, the upper-level configuration changes. A ridge weakens, shifts, or is eroded by surrounding flow. A trough develops in a new position. The path available to Atlantic cyclones changes with it. When that happens, a region that spent days or weeks under relatively settled weather can suddenly find itself exposed to a much more mobile pattern. That does not mean the atmosphere is releasing stored heat in some dramatic discharge. The physics is more subtle. The atmosphere is constantly redistributing heat and momentum. Waves in the jet stream grow, move, interact, and decay. Surface pressure systems respond to that evolving three-dimensional flow. Late August provides a good example of how quickly the map can change. The Baltic storm of August 22nd and 23rd was a dramatic episode within that changing circulation. But one storm is not enough to declare that Europe has entered a permanent storm phase. And it certainly does not tell us exactly what the entire autumn will look like. That leads to the next question. Does this mean autumn 2026 will be unusually stormy in Europe? The responsible answer is that we cannot know that with confidence from this event alone. Weather forecasting works on several very different timescales. A forecast for the next few days can be highly detailed because the current state of the atmosphere is already observed. Meteorologists know where the major lows, highs, fronts, and jet stream features are located, and numerical models can calculate how they are likely to evolve. As the forecast extends farther into the future, small uncertainties in the initial state grow. Around a week or more ahead, ensembles of many model runs become increasingly important because they show a range of plausible outcomes rather than one guaranteed future. A seasonal forecast is different again. It does not attempt to tell us whether it will rain in Paris on a particular Tuesday in October. Instead, it estimates whether broad conditions over a region are more likely to be warmer, cooler, wetter, or drier than average over a period of weeks or months. And climate projections operate on an entirely different scale. They describe statistical changes over decades, not the exact weather on a particular day. Confusing those timescales creates many of the misleading claims we see about future weather. There is another large-scale factor in the background during 2026, El Niño. El Niño develops when the central and eastern tropical Pacific become unusually warm, and the atmosphere above the ocean reorganizes in response. Its influence can extend far beyond the Pacific through changes in global atmospheric circulation, but its effects are not equally strong everywhere. For Europe, the relationship is less direct and less reliable than it is in several other parts of the world. European autumn and winter weather depends heavily on what happens over the North Atlantic. The position of the jet stream, the behavior of blocking systems, the storm track, and patterns such as the North Atlantic Oscillation. The North Atlantic Oscillation, or NAO, describes changes in the pressure difference between the region near Iceland and the subtropical Atlantic near the Azores. When that pressure contrast is strong, the Atlantic flow can become more vigorous and more zonal, often favoring a more active west-to-east storm track toward northern Europe. When the contrast weakens or reverses, the circulation can become more meandering, and blocking patterns may become more important. But the NAO itself can change substantially from one month to another, and is difficult to predict reliably far in advance. So even if the tropical Pacific provides some seasonal background influence, it does not give us a simple answer for September, October, or November in Europe. We can talk about probabilities. We cannot responsibly promise a specific sequence of storms months ahead. There is also the Atlantic Ocean itself. When ocean temperatures are unusually high, exchanges of heat and moisture between the sea and the lower atmosphere can change. For extratropical cyclones, however, this is only one factor among many. Their development is fundamentally connected to atmospheric temperature gradients and upper-level dynamics. Even systems that contain remnants of former tropical cyclones can evolve in very different ways as they enter the mid-latitude circulation. Some intensify, some weaken. Some change track and never approach Europe at all. A warm ocean can modify the environment. It does not determine the outcome by itself. That idea, separating background conditions from the trigger for an individual event, is central to understanding what happened in late August. Return to Riga, Lithuania, and northeastern Poland after the storm. The fallen trees, damaged roofs, disrupted electricity, flooded streets, and transport problems were concrete consequences for real communities. But behind those visible impacts was an atmospheric system governed by processes that are understandable. Pressure gradients drove strong winds. Fronts organized the movement of warm and cold air. Moisture was concentrated into rain bands. The upper atmosphere helped steer and develop the cyclone. And the larger European pattern determined which regions were exposed to that system and which were not. One severe Baltic cyclone does not prove that Europe's climate has suddenly entered a completely new state. A single weather event is not a climate trend. Climate is statistics accumulated across many events and many years. But an event like this can reveal the mechanisms that shape European weather every day, even when they are less dramatic. Temperature contrasts, moisture, the oceans surrounding the continent, the position of the jet stream, high and low pressure systems, and the movement of the boundaries between different atmospheric regimes. Perhaps that last point is the most useful way to think about Europe in late August 2026. The story is not simply that Europe is becoming hotter. It is not simply that storms are becoming stronger. And it is not that every region is moving in the same direction at the same time. The more interesting question is how the background climate interacts with an atmosphere that remains highly variable from day to day and region to region. A warmer atmosphere changes the amount of moisture that can be available. Warmer seas change the environment beneath passing weather systems. Dry soils can intensify heat locally. But the exact weather experienced by a particular city still depends on circulation, on where the ridges, troughs, fronts, and storm tracks happen to be. That is why the map can change so quickly. And it is why two apparently opposite headlines, drought in one part of Europe and destructive rainfall in another, can both be true at the same time. The weather over Europe at the end of August 2026 does not tell one simple story about heat or storms. It shows something more complex. Different atmospheric regimes can exist side by side across the same continent, and the boundaries between them can move rapidly. To understand those transitions, it is not enough to look only at the temperature outside. You have to see the whole system: the ocean, the moisture, the pressure patterns, the fronts, and the jet stream high above them. That is where the answer begins to emerge. And that is where we need to look if we want to understand not just what the weather is doing today, but why the entire pattern can change faster than it seems.